Study glycogen. Before studying glycogen, right? We want to understand what is glycogen. We want to understand where it comes from, why it exists. Every possible, we just want to look at glycogen in all the possible views, right? We want to look at it and we want to think about it, right? That's it. So, before even we talk about the topic, we want to know where it comes from, right? So this is glycolysis. Glycolysis is basically when you break the glucose, right? And when you break the glucose, you get some product, right? Here the glucose is called a substrate, and the products you get are pyruvates. We get 2 molecules of pyruvate, you get 4 molecules of ATP, you get 2 molecules of NADH, and you get some water, right? When you break down a 1 glucose molecule, okay, and you do it in glycolysis, and glycolysis is a anaerobic, okay. You don't use oxygen, you don't have any oxygen in this process, so that's why when you break down this process you get just 4 ATP. That's why the ATP is very less, right? But the thing with glycolysis is that it's very fast, so cancer loves it. And when you're working out, when you're exercising, you also do this glycolysis, okay. So the thing is, how would you know? How would the glucose, the first question is, how would the glucose know that should I go into glycolysis or should I go into the process that we're going to study, that is called glycogen synthesis, okay? How would you know that? It really depends. So the answer to this question, it really depends upon the availability of oxygen. But when the oxygen should be available, that's another question, right? So the answer to that question is in step number first, right? So in step number first, in glycolysis, the glucose goes through an enzyme called hexokinase, or it can go through another enzyme called glucokinase. Now, hexokinase and glucokinase are 2 different enzymes. Hexokinase is present everywhere, almost, in your muscles, right? Everywhere, in your brain, everywhere. But glucokinase, on the other hand, it's only present on the liver, and it's only present on the pancreatic beta cells, right? Now, I must be asking why it's present. Well, hexokinase has different function. Hexokinase is meant for glucose entry and glucose capturing, while you are not eating, all the time, literally 24 hours, right? And glucokinase is actually responsible to trap glucose only when you have big meals, okay? And doing that actually protects you from these insane and big glycemic surplus, hyperglycemia. It protects you from this hyperglycemia that you can get if you don't have this glucokinase, right? Imagine you just had a big meal and you don't get big surge in glycemia, right? But because liver actually acts as a buffer, not as a competitor when it comes to glucose, right? So that's why you have glucokinase. Okay, never mind. Let's go to the glycogen synthesis, right? So once glucose goes under hexokinase, hexokinase puts a phosphate on glucose, and the result is glucose 6-phosphate. Why? Actually, because glucose wants to stay in the cell, right? Glucose is super duper water soluble, right? Your blood is actually just water, right? So glucose can freely move inside and out through these transporters called GLUT, right? It can move. And the thing is that if you want to keep the glucose inside the cell, you want to have something called hexo or gluco that will put these negative charge on this glucose that will actually make the glucose super duper polar. And once it's polar, once it's charged, it's gonna stay inside. It's gonna get stuck inside. Not gonna stay inside, it's gonna get stuck inside. Now, once the glucose is in this form called glucose 6-phosphate, the question arises. Now is the point where glucose has to make a choice that should it shunt into glycogen synthesis, should it go into glycolysis, or should it go into pentose phosphate? So we have these different choices. Now it can go into glycolysis once it has enough this enzyme called PFK1, that is phosphofructokinase 1, right? What it does is actually puts ATP on the glucose, and it actually Kind of, it's a weird way to say, but a PFK1 enzyme commits this glucose 6 phosphate to stay in glycolysis. So availability of PFK1 and enough ATP store makes glucose 6 phosphate run in glycolysis. But if we don't have these two things, and we have abundance of oxygen, the glucose 6 phosphate will actually shunt into glycogen synthesis pathway. And this is what we are going to study today, glycogen synthesis pathway. We're not going to study pentose phosphate pathway because we have different conditions right at these moments, right? So let's just deal inside this glycogen. So we will start from glucose 6 phosphate. Okay, so let's go and let's just start, right? That's important. Okay, so glycogen. Now in this whole video, in this whole thing, right, we're gonna study a lot of things. So let me write you what we're gonna study, right? We're gonna study glycogen synthesis, right? We're gonna study phosphorylase, we're gonna study protein kinase A, glucagon, insulin, and CAMP, right? So we must understand these fundamental things so that we understand why the glycogen exists itself, right? Now to understand everything, right, we have to deal deeply, right? So let's start, right? Now I want you to imagine that evolution is, or maybe God is creating the first human, right? Now the first question is, should human, or this woman or man, should human store energy? The first question is that. Should, we are just thinking, right? I am thinking, should a human store energy? That's a good question to think, right? Should you? And the answer is, of course, yes, right? Of course, yes. But now another question arises. Now, how will you store the energy, right? But now the question is not why. The question is how right now. How? Now think before answering, right? There are like a lot of choices. You have glucose itself, you have fat, you have protein. I mean, every bond in chemistry has some energy stored, right? So which bond are the best bonds, right? I mean, is it ATP? Is it glucose, right? Now we have a lot of choices right there. Body stores energy in multiple ways: ATP, glucose, glycogen, fat, protein. Now we can ask like why these 5 types or 7 types or 8 types of energy distribution bonds exist, or we can just ask like why don't just glycogen exist, right? Why did evolution chose these different ways to store energy, right? The answer to this question is actually because all these different forms of energy solve different problem, right? Let's talk about ATP first. ATP. What is ATP? Right? A lot of people think that ATP is energy, right? But why not just, what is ATP first of all? ATP is adenosine triphosphate. What's really happening here is that we have adenosine, like this protein, right? Adenosine. And then we have these phosphate bonds, and we have 3 phosphate bond on adenosine, right? And then when we bond the phosphate with adenosine, we actually create a bond, and this bond actually stores the energy, right? When we break the bond, we get the energy, right? That's why to get some energy from to get some energy from ATP, the ATP transforms into ADP, and then you can break it once more time, and then you'll get something which is called as AMP. Right, that's the last form, right? So ATP is tri, D is duo, or a duo, right? And M is mono right there. So I hope you understand. So ATP is just a molecule and it stores some energy, right? Now, a lot of people know that already, right? Now, why not just make millions of ATP molecules, right? Why not, right? Why not just make, let's think about it. Because that's how I think. I think ATP is like a cache, okay? And the thing is that cache can be very tough to store if you have millions and billions of it, right? Now, imagine you receive like $50,000, right? Inside your pocket. Are you gonna keep it? No, you cannot keep $50,000 in your pocket. You can't carry it, right? So why not? Because it's too safe. First of all, too unsafe, right? It's too bulky, right? It's not stable. You spend it like quickly. So instead, most of the money actually comes to your bank account, right? And only small amount stays in your wallet. So ATP actually is like a cash. I call cash. Cash is the king and ATP is king, right? So ATP is the fast immediate cash, right? So ATP is meant to be used immediately. That's what I'm trying to put the thought into you. ATP is constantly changing its form from ATP to ADP, ADP to again ATP, ATP again to ADP, right? This thing keeps on happening, and it happens like thousands of times in 1 second, right? So it's not a long-term storage molecule. It's a energy currency. It's a cash, right? Now, you can ask me, well, Shashwat, how much ATP does an average person like me who is viewing this video use per day? Well, it depends upon your body weight, I think, right? Because ATP molecules are like continuously synthesized and continuously recycled, right? Now, if you weigh like 70 kilograms, you may recycle around 70 kilograms worth of ATP every day. Now, the same ATP molecules are being like used all over again and again. So therefore, ATP is the immediate spending cash or money, whatever you want to call it. It's not a saving account, right? Now, why don't we just store glucose, right? I mean, we have glucose. You eat glucose all the time, right? You eat chips, you eat potatoes, you eat rice every day, right? Why not just store the glucose, right, in this big form, right? What is glucose? Glucose is C6, carbon 6, C6H12, and O6. So it's a big molecule. It's a big molecule, and it's super duper high in energy, right? Why don't you just store that? Let's simply store glucose. Seems logical. The question is, why not? Well, turns out that, let me write this first, glucose. So why not just store that, right? That's a good way to think it. Let's just store it. But why can't we store it? Turns out that it's tough to store glucose because the thing with glucose is that glucose is very water soluble. That's the problem. It's very much soluble in water, right? Now, imagine two compartments, right? Okay, to teach you that, to learn that thing, we have water right there. And then we have cell membrane right there, right? That's a cell membrane. Cell membrane, okay? And then we have sugar here, right? Now, we have two compartments. This is compartment number 1. This is compartment number 2, right there, right? The question is, can water cross the membrane? Can water cross the membrane to meet sugar? Absolutely yes, turns out. Absolutely, because water tries to equalize the concentration difference. This movement is called something which is called as osmosis, simply, okay? Osmosis. Osmosis, what is osmosis? When water tries to equalize the concentration gradient in both compartments, that's called osmosis, right? Now, from osmosis, I want to derive something which is called as osmolarity. Osmolarity. Now I come to osmolarity. Now, what is osmolarity, right? What? Now, osmolarity is the answer when you ask that what exact factor will determine where water moves. Now, it's not weight, it's not molecular size, it's actually the number of dissolved particles. That's the answer. Now, one glucose molecule count as one particle, okay? One glucose molecule count as one particle, okay? So if you have 10 glucose molecule, they'll count as 10 particles, right? Water will respond with this osmolarity, right? Water will respond to the particle number, not chemical identity. Now the question is, suppose the liver has this, suppose, just imagine the liver, your liver has like a, I don't know, 10 million 10 million separate glucose molecules. 10 million glucose molecule, right? It has a lot of glucose molecule. What happens now? What would happen? Inside the liver cell, the particle concentration is like enormous, right? It's storing this 10 million glucose inside. What's going to happen is actually water is going to move inside and the cell is going to swell up, right? And the cell membrane is going to stretch and eventually the cell can actually get ruptured because of the catastrophic amount of water that's going to move inside because of the concept of osmolarity. Okay, so I mean, storing glucose, it's shitty. It's just bad for the business. It's just bad for the osmosis. It's just bad for it. Then how can we store glucose, right? We can't store glucose in molecular way, right? Can't glucose in a particle way. Let me write it. Particle. Can't. Then how can we solve this problem? The nature solves it already, right? I mean, I already thought about this, right? Then how will we solve this? The glycogen solves this problem, actually. This is the answer why glycogen exists. The thing is that one glycogen molecule, right? Imagine now, okay? Now imagine, instead of one glycogen molecules, how many glucose molecule does it contain? That's the thing, right? Now, the thing is that you'll be very much shocked that one glycogen molecule actually contains thousands of glucose. It's cool, right? It's amazing. Thousands of glucose. Sometimes 10, sometimes 5, right? But the question is, how many particle is glycogen then? I mean, actually, it's just one. Right? We still have one particle. So we are actually playing with the osmosis rule here, right? Right? That's amazing. This is amazing, right? So free glucose is like 10,000s, right? Thousands of glucose. But you put that in one glycogen particle, right? Huge difference. But the amount of stored glucose is same. Massively different osmotic effect we'll see, right? This is amazing. Now, that's one solution, right? Now, the problem number 2 with glucose is that glucose is very, very, very reactive, right? Is glucose harmless sugar? What do you think? I mean, you have diabetes, you have these retinopathies, you have this neuropathy, you have these problems, you have atherosclerosis. We have these massive problems with just diabetes disease. Why it's happening? Because of sugar. Sugar is very reactive. That's the thing. Sugar contains something which is called as aldehyde group, right? I'm talking about glucose right there. I mean, we all know that glucose is very notorious for making bonds, right? Glucose is responsible for the disease called diabetes, right? But did we care to know why? And it turns out that glucose has something which is called as aldehyde, an aldehyde group, right? Let me write it down. An aldehyde group. That's the thing. So glucose has that. And the thing with aldehyde group is it's actually, where is aldehyde group? You can ask me. It is in its open chain form, right? Now, why am I even telling you about this? Because this aldehyde group is the reason why glucose reacts with proteins, right? This is the reason. This aldehyde group is the reason why glucose talks to proteins or react. So here we have this aldehyde group, right? And it's the reason why it can bond with protein. And this makes glucose very much reactive. We call this property, or we call this process, as non-enzymatic, because we're not using any sort of enzymes, right? Non-enzymatic glycation. Okay, we call it non-enzymatic glycation, right? So what are we talking about now? We are talking that glucose is super duper reactive, right? Now, clinically, right? What molecules, clinically, like we are thinking about clinical now. Clinically, what molecules measures long-term glucose measure, like long-term glucose exposure, right? We call that something which is called as HB, HbA1c. That's we call this thing, right? And the thing here is that we are actually trying to measure glucose binding to hemoglobin. Now, hemoglobin is a protein, and this whole thing happens because of this aldehyde group. Okay, this aldehyde group is the reason why we can measure something which is called as HB1AC, right? This is the thing that we use. Okay, so now imagine you are storing this huge amount of free glucose inside a cell, right? What would happen? You would have these unwanted glycations, right? Now we will have these non-enzymatic glycations, right? What would happen later on is that you will have these protein dysfunction and then cell damage and then just messed up things, right? So nature doesn't want that too, right? That's problem number 2. That's the problem. Now, what nature or what God did actually is that glycogen actually protects against the both problem. Glycogen is the solution for both of the problems. Let me make it a box. So we solved this error, and we solved this error too. And it solved the osmotic problem and it solved the aldehyde problem, right? But why not store everything as fat then? Then that's also a question, right? Fat is also incredibly high in energy, right? I mean, fat contains much more energy, right? I mean, do you know that 1 gram of fat has 9 calories, right? And carbs actually have just 4, right? So 9. So I mean, fat is incredibly high in energy. Why don't we just keep everything as fat then? That's also a question. Because the problem with fat is that fat is slow. That's the problem, right? So imagine you're just running. Imagine you're like running fast, right? You're Usain, whatever. You're like a runner. You're like a sprinter, right? You're running, and what happens? Suddenly you start running. What happens? Can these fatty acid chains be oxidized? We call this oxidation. Breaking these fatty acid chain, we call them oxidation, okay? So can the fatty acid oxidation immediately provide enough ATP? It turns out that the answer is no, all right? Because fat oxidation requires, first thing, oxygen, because it's an oxidation. Second, it involves mitochondria. A lot of your cells don't have mitochondria, such as RBCs. And the thing with oxidation is that it's a slow process. It increases ATP gradually, right? So that's the problem with fat. So what's the problem with fat? Fat is, first of all, it needs oxygen, right? You don't have oxygen all the time, right? It needs mitochondria. You don't have mitochondria in all the cells. That's also a problem. And the last problem is that it's slow. You need something fast. Imagine you're like stuck in a forest and you see a tiger. You are gonna run for your life, and this running for your life is gonna be done not because of fat, I am sure. If you had just fat, you are cooked, I should say. Okay, so fat, that's the problem with fat. Now, glycogen. Let's come to glycogen. Glycogen is an emergency fuel. That's how glycogen is. Okay, that's how it is. So think about it. Wallet. You have a wallet, right? That's your ATP. You have a checking account and you have a saving account. ATP is the cash in hand, okay? Glycogen is the checking account. You can just access this checking account fast. You can just go to an ATM and take some cash out. Fat is that savings account that you don't want to touch, because you know you'll get much better return if you keep it in fat. That solves the first question, that why do we have glycogen, right? That's the first question. All right. Now, that's the first question. Why do we have glycogen, right? That's simple. So the first question was why, and we answered it. Why? Because it solves a unique set of problems. That's why. Now, you can ask me second question, Shashwat, where exactly is this glycogen stored, right? Turns out, let's just think about it again. Where do you think glycogen is stored? Do you think every cell has a private glycogen store? Do you think? No, mainly liver. Mainly just liver. Liver has a glycogen store. And what other type of cells do you think would need this emergency cache? It's called skeletal muscle. Skeletal muscles. Because you need this, right? You want to run fast. You need to have energy right there at the right moment, right? Now, why these two only, right? Because they solve this physiological problem, right? The thing with liver is that we have this thing, liver glycogen, right? Now, who benefits from liver glycogen? What do you think? Whole body, because liver is amazing. Liver breaks down this glycogen really, really fast and releases glucose into the bloodstream. Now, it uses this enzyme called glucose 6 phosphatase, right? What does it use? It uses glucose 6 phosphatase. Now, this enzyme removes that phosphate that was put by Mr. Hexokinase earlier in this video. This hexokinase and glucokinase put this phosphate on the glucose, right? And then when the glucose wanna get out, we use this enzyme called glucose 6 phosphatase. It's a tase. It removes this, right? So phosphatase. It removes the phosphate group from the glucose, right? Now, liver protects brain, right? RBCs, kidneys, everything, because everything is dependent upon glucose, right? You're sleeping, you have like fasting for 12 hours, you have not eaten anything. Do you think are you going to survive? Of course, because your liver is there. Your liver is going to use this enzyme called G6 phosphatase and going to remove that phosphate from the glucose, and you will have glucose into your brain, into your muscles, everywhere, right? What about muscle? What about skeletal muscle? Well, this skeletal muscle, right? Can the muscle release glucose into the blood? What do you think? Is it relevant? Is it good for the body, for muscle to do that? No, actually. Why can't the muscle do that then? Because muscles don't have this enzyme called G6 phosphatase, right? So there is no connection here. There is no connection. No, it can't. That's why it can't. Therefore, muscle glycogen is used up only by that specific cell of that muscle. It cannot raise blood glucose levels. Now, why would the evolution design this? I mean, amazing design, right? Imagine you're exercising and your leg muscles is like, your leg muscles are working like intensely. I mean, we hate working out the legs. I mean, I hate it. But should they keep exporting glucose to the blood? No, because leg muscles need them, right? They need it themselves. Therefore, muscle glycogen is a local fuel, right? So it's a local fuel. And liver glycogen is a whole body fuel. Okay, so we understand this little bit of fact. Now, I know my lecture or my study session is very long, but that's the key of it. If you keep it long, you'll understand deeply and you'll understand the reasons of why, basic whys, right? Okay, now we understand the reason of why and where, right? Now let's understand how. That's also important, right? That's actually very important. Okay, let's build it now. Let's go there. I like this space a lot. Let's ask ourselves, how? Pidaras. Oh, okay. How? Let's ask ourselves, how glycogen is made, right? That's the whole theme of the video, and it's been 30 minutes now. Now I come on the topic. Now, we call this process of synthesizing as glycogenesis. First of all, that's the basic thing. Okay, let me start now. So we call this glycogenesis. So glyco means glucose, genesis means creation, therefore glycogenesis, right? Now, when should glycogenesis occur? First question. Of course, after the meal. If you don't have glucose, you will not make glucose, right? And you need glucose for glycogenesis. Other thing that you need for glycogenesis is called insulin. Now, why? Because when insulin is high, you have glucose that can be available. That's the thing. So, when? Well, first is after the meal, right? After meal, and you need a good insulin response. Insulin. If you don't have insulin, you will not do anything, because this glucose that will be available after your meal will kind of waste, right? Because if you don't have insulin is the hormone that lets the glucose be available inside the cell. It lets the cell gulp up that glucose, right? So we need two things to have that synthesis of glycogen. Okay, again, so we need these two things, right? Now let me talk about something called as glycogenolysis, okay? Because this is very important. Let me just put that thing. Now you must be thinking, oh, we are going away from the topic. No, we are not. We're going away from the topic. I'll tell you why I'm telling you. Glycogenolysis, right? Again, break the word. Glyco means glucose. Lysis means breakdown. So we want to break the glycogen, right? So glycogen broken down into glucose, and the energy is released, right? Now, when should the glycogenolysis happen? Of course, when you're fasting, right? Or when you're exercising or stressed, right? That's when the rapid glucose availability is important, right? So it's just simply when your glycogen breaks down to glucose, and then glycolysis can happen, and then we can get ATP. Okay, simple, right? Not so complex. Now, I want to answer another question. Now, why are glycogenesis, that's the formation of glucose, right? Why glycogenesis and glycogenolysis, this enzyme, this process, right? They never fully are active together. Why don't they happen? Why both of them are not actively together, right? Because imagine you build a house, at the same time another crew comes and destroys it. That's like wasteful. Body avoids that, right? So when one pathway is activated, maybe glycogenesis is activated, then this glycogenolysis will be shut down. That's the thing. So one pathway is activated while the other is suppressed. This is always how it is, right? And this is exactly how phosphorylation acts on molecular switches. Now we'll come to that pathway later on. Now you can ask me, under what conditions does this system actually fail, right? When? Because when can it fail? Because that's how you want to think, right? It turns out that let's just imagine, right? If glycogen didn't exist, that would be a big problem for us. Could humans survive overnight fasting? No, absolutely not. Because liver would have very little available glucose reserve, and blood glucose will just fall, and then you'll just go to a very deep sleep and you'll never wake up. What if liver just stored free glucose? Well, your liver will just swell up and you'll die. What if muscle release glucose into the blood? Well, then you will not be able to run when you have a lion behind you. What if fat was the only resource? Well, same story. You saw a lion wants you, but you don't want that lion, but you want to run. Oh, turns out I just have fat. I'm so fat, I cannot run. So that's the thing, right? Now we will come to the actual metabolism, glycogen metabolism, okay? Now let's start learning, right? Let's start this whole thing by asking simple questions again, right? A lot of people will think that we have glucagon, then we have CAMP, then we have pKa. We don't understand much of it, right? But I'm just introducing you these words. We have something which is called as CAMP, CAMP, right? Cyclic AMP it's called, okay? Then we have pKa, then we have phosphorylation, whole cascade, right? Now, a lot of people will yell, oh, what are these enzymes? Okay, even before I introduce you to these names, let's just think, right? Let's ask the biggest question in the whole topic, right? The thing is, if you have not eaten for like last 14 hours or 12 hours, what do you think? The blood sugar will fall or not? That's the first question, right? The answer is, of course, it will fall, right? Now, second question is, okay, it's gonna fall, but how will the liver know that it's falling, right? That's also a question, right? Because we know that liver is responsible to maintain the blood sugar when you're fasting. But how the liver would know that your blood sugar is falling? Can liver cells measure blood sugar directly? No. Instead, what happens is that we have this pancreas, little tail pancreas, right? This pancreas actually senses all these changes, right? The pancreas in your body is the glucose monitor. That's the statement, okay? So pancreas is the glucose monitor, and it is responsible for talking to liver, right? It's like a thermostat. It doesn't produce heat, it just detects temperature. Then it tells the furnace like, hey, turn on the furnace, right? That's how you say it. And pancreas behaves similarly, right? And it constantly measures your blood glucose. Now, what happens when your blood glucose falls, right? Imagine your blood glucose falls. Which pancreatic cell is gonna detect it? Turns out, alpha cells. A lot of you guys might have thought about beta cells, but not. So pancreas is the glucose monitor. Which cells? Alpha. Which cells? Alpha cells. Alpha cells. So alpha cells is the cell that is responsible for your monitoring of this whole situation, okay? Now you'll ask me, well, why not other cells, right? Well, alpha cells. Alpha cells, why? Because alpha cells have an enzyme which is called as glucagon. Glucagon. That's a cool name, right? I love this name because it's so simple. When glucose is gone, alpha cell produce glucagon. Beta cells, on the other hand, produces insulin. And then we have delta cells. Delta cells produce something which is called a somatostatin. It stops all everything. It's like a handbrake on your car, right? Now, why glucagon, right? And what message the glucagon is sending? What's the deal with glucagon? Who is this guy? Well, let's first of all, glucagon actually sends the message that, hey, your body is entering into a fasting state. So glucagon tells the body that, hey, your fasting state is on. That's what glucagon does. Now, what should the liver do when it gets this message from the glucagon? Well, turns out liver stops storing the glucose now. Liver actually starts releasing glucose. So glucagon tells the liver that, hey, the fasting is on, and now liver starts releasing this whole trapped glucose. Okay, so the first step is glucagon, right? The first step is glucagon. Okay, so glucagon acts on liver. Now, why does it specifically say liver? What do you think? Why am I even saying liver? Because I already talked about that stores, right? Where the glycogen is stored. Well, liver, right? Because liver is the primary glycogen store. That's why. Hepatocytes, exactly, to be named. And it has a very little direct effect on skeletal muscle. The glucagon effect is not non-existential on skeletal muscles, right? They can ask you like, hey, does glucagon talks to skeletal muscle? No, it doesn't. Now, why doesn't muscle respond to glucagon? I mean, suppose you're fasting, right? Should the muscle consume its own glucagon? Of course it does, But should the muscle also release glucose into the sugar? No, into the blood. No, of course not, because muscle don't have this enzyme called glucose 6-phosphatase, right? It cannot export this glucose efficiently inside the bloodstream. So that's why glucagon has a very little effect on these muscles, right? And so how then okay, glucagon doesn't talk to muscle. Then what talks to the muscle exactly, right? Then who is the chit chat partner of skeletal muscle? It is called epinephrine. Epinephrine can talk to skeletal muscle, right? So epinephrine can talk to skeletal muscles. Now the thing with epinephrine is that epinephrine can actually talk to both skeletal muscles and liver cells and hepatocytes, right? You can ask me, why both? Because imagine you're like under an attack. The tiger is chasing you, right? Do you think now the question is, do only liver cells need to respond, or the whole body needs to respond? The whole body needs to respond, right? Muscle needs that ATP immediately. Liver needs to maintain the blood sugar, right? So both of these organs will respond to epinephrine. So epinephrine is that global body, a whole body signal sender, something like that. Okay, I don't know how to put it in words, but that's how it works. So epinephrine can talk to both of them, and epinephrine is the guy who tells your body that, hey, you are under attack, maybe run, right? So both organs can respond to epinephrine. So that's the thing. So liver responds. So when epinephrine talks to liver, right? What happens? Liver releases that glucose and maintains that blood sugar levels. Okay. What happens when muscle talks to epinephrine, right? The response that skeletal muscle generate is that they generate that ATP, and they generate ATP for what? For contraction. And once you have that contraction, your local glycogen storage break down, and right, same thing. So same hormone, same epinephrine, but different effect, right? And that's what I'm going through, right? So same epinephrine, but different shit, right? Now we know that here I'm gonna introduce you to another thing. This glucagon, right, is gonna talk to someone else now. We have new character. This character is called adenyl. ADENYL, adenyl. Adenylyl cyclase, CYCLASE, right? So we have this now new character. Now he's gonna talk to our glucagon. So first question, what is this adenyl cyclase? What is even cyclase? Sounds like a superhero, right? Well, there are two parts in this whole word. We have first part, that's cyclase, and we have first part that called adenyl, I don't know how to call it, and second part is called cyclase. Now, what is cyclase? Cyclase is an enzyme whose job is to form a cyclic molecule that specifically converts ATP into CAMP. So cyclase does what? It converts ATP into cyclic AMP. But wait, now the question is, why is ATP being used? Remember, ATP is not just energy, it also serves as a raw material. And even we saw even in glycolysis that ATP is used for a lot of processes, right? So ATP here is used by cyclase to produce, which is something called as cyclic AMP, CAMP or cyclic AMP. Now, why are you exactly creating CAMP, mister? Right? Why do we need CAMP? I mean, there must be some reason, right? Don't you think so? Right? Why are you creating CAMP? That's a cool question. Okay, how would I tell this? Imagine there's a king, right? That king never personally visits every citizen, right? Instead, what he does is he sends these messengers. Now, hormones work in a similar way. Glucagon is that king, right? Glucagon is that, no, opposite. So sorry. Glucagon is that messenger inside the cell. CAMP becomes the second messenger, okay? So glucagon is the first messenger and CAMP is the second messenger. Okay, so first messenger versus second messenger. Now we are on this level. So glucagon versus CAMP. Okay, first messenger outside the cell, that is called glucagon, right? Second messenger inside the cell, called CAMP. So it's where? It's inside the cell. Right? Now, CAMP, right? That is very important. I hope you can understand me now. Now, you can ask me, hey, Shashwat, you talk so much about glucagon. Why don't you just make glucagon cell soluble? I mean, why can't glucagon just go inside the cell? You know, what's the problem here? Why not let glucagon enter the cell? Why use CAMP at all? What's the use? Why are we even using second messenger, right? Because the glucagon is a peptide hormone. That's the thing. It's a protein hormone. Okay, so it's a peptide hormone. It's a peptide hormone. So that's why it cannot cross your cell membrane. Peptide hormones are largely hydrophilic, right? Hydrophilic means they are very much water soluble. They cannot diffuse through a lipid, that is fat membrane, that your cell has. Instead, what they do is they bind to the receptors, and those receptors that are present on the cell membrane create this CAMP itself, CAMP, CAMP. Now the question is, what does CAMP actually do then? Well, CAMP, think of this CAMP as an emergency text message. Hey, activate the fasting program. This guy is going on a fasting journey. That's what CAMP exactly does. It talks. Okay, so CAMP talks to whom exactly? CAMP talks to something which is called as protein kinase. Kinase means it puts the phosphate. Okay, kinase A. That's what Mr. CAMP talks to, or Miss CAMP talks to, whatever you want to call it. Okay, so it talks to protein kinase A. Now, what is kinase? I mean, already, let's break the word down. Kinase actually means something that adds a phosphate. Remember, kinase means adds a phosphate, right? Phosphatase is opposite. Phosphatase is removes phosphate. Whenever you read the word ase anywhere in biology, it means it takes down that thing, okay? So, protein kinase A, called pKa, right? This pKa. Now the question is, what is protein kinase? Because what it does, what is it doing, right? What do you think? What pKa is? Well, pKa, protein kinase A, actually phosphorylates what? Phosphorylates proteins, because it's named protein kinase A. This enzyme adds a phosphate on protein, right? What activates it? CAMP. So CAMP activates protein kinase A. Now protein kinase A adds a phosphate, PO4 negative, on a protein. Simple, right? Because the name says so, right? Now, why doesn't the glucagon directly phosphorylate these enzymes, right? These proteins? Because signaling needs amplification. That's the reason. The glucagon, cannot put a phosphate on protein because the whole signaling of glucagon needs something which is called as amplification. Now, this is a very cool word and very cool concept. It cannot talk to because it needs amplification. That's why this whole mess is there. It cannot put that phosphate on the proteins. It will not, because whole signaling, whole biology needs these amplifications of whole message, right? Imagine you have one glucagon molecule, right? It activates this one receptor of CAMP that is responsible for formation of CAMP, right? It produces, what happens is that it produces these multiple molecules of CAMP. Now, each CAMP will activate one pKa. So each pKa phosphorylates many protein. This is called signal amplification. This is exactly how it sounds, right? It needs this amplification of signal. It just gives the signal like, hey, do that. Now you want big quantities of things to happen, right? You don't want to just let just once. You don't want what you don't want. You don't want one signal to produce one product, right? What you want is one signal to produce multiple product. That's what you want. And that thing is called, what is it called? It's called signal amplification. Simply. So simple, right? I think it's very simple. So that's what protein's signal amplification is. Now, why amplification is important? I just answered you, right? Let's come back to protein kinase A now. We are on the protein kinase A. Now, pKa phosphorylates a lot of proteins. A lot of proteins are a lot of enzymes, right? Because these are interchangeable things here, right? So pKa phosphorylates a lot of enzymes. That's a statement, that's an assumption. But why does it do it? Because fasting requires a lot of multiple coordinated changes. You just don't want one glycogen breakdown. You want everything to be coordinated together. So the first target is protein kinase phosphorylates what? Glycogen phosphorylase kinase. That's the thing, right? Let me break down. You must be thinking, what the hell did he even say? Okay, let me delete that now. Let me put that thing in here. Okay, so first target is what? Glycogen phosphorylase kinase. It's also a kinase. He also phosphorylates something, right? So glycogen means, glycogen is related to glycogen. Phosphorylase means an enzyme that breaks down glycogen. Phosphorylase. Okay, let me write something. This enzyme, phosphorylase, is actually responsible for breaks glucose. Okay, this enzyme, phosphorylase, okay, this enzyme breaks down glucose. What about kinase? Another kinase we have here. Kinase is just puts the phosphate, right? Activates another protein by phosphorylation, right? Phosphorylation, just adding that phosphate to anything, to something, is called phosphorylation, simply. Okay, so kinase, right? That's phosphorylation. Now, there's this hierarchy, right? Right? So glucagon talks to adenyl cyclase. Then cyclase produces this cyclic conversion of ATP into cyclic AMP. And then this cyclic AMP talks to protein kinase A. And that's protein kinase A phosphorylates, puts the phosphate on this enzyme called glycogen phosphorylase kinase, right? This is what is happening. And this last enzyme that we call it glycogen phosphorylase kinase actually is the enzyme that is responsible for breaking down of something called your glycogens, right? That's how the glycogen breaking down works. So each enzyme activates the next. We call this whole thing as something which is called as what? Kinase cascade. Simple name. Because we have a lot of kinase right there, right? This whole thing starting from glucagon and ending in what? Ending in glycogen breakdown. Glycogen breakdown, right? This whole thing, we call this whole thing as what? We call this thing is kinase cascade. Let me write there. Let me write it down somewhere. Right. We call it what? Kinase cascade. Because it's a cascade, right? It's happening in front of you. I think it's amazing how it happens. I find it very beautiful how it really happens. Now you must be thinking, wow, Shashwat, that's a lot of steps. Step number 1. That's a lot of things happening. Right? 1, 2, 3, 4, and 5. And then 6 itself, right? Well, actually, multiple steps actually is really great for the cell because it gives the cell this regulation. It gives fine control on each step, right? Each step can be tuned. Each step can be changed. That's why we have multiple steps. Let's talk about glycogen phosphorylase. This guy, okay? This is an enzyme that actually performs the glycogenolysis. This step. Okay, so glycogenolysis happens because of whom? Because of glycogen phosphorylase kinase. Now, question, what reaction does it perform? What's happening chemically, right? What happened here is that it removes that glucose residue from glycogen by breaking these alpha. What's happening here? Let me write it down. It breaks down this alpha 1, 4 glycosidic bonds. Glycosidic bonds. Right? Through what? Through phosphorylase. Through phosphorylysis. Wow, that's a cool name, right? It does this whole thing called phosphorylysis. Right? Now, what is this phosphorylase? Phosphorylysis. This is a process in which we use that PI, that is inorganic phosphate, and we remove that, right? I mean, we use this inorganic phosphate and we produce this thing which is called as glucose 1-phosphate. In the end, we produce something which is called as glucose 1-phosphate. That's what we get. Now, the cool thing here is that we are not getting free glucose here. We are getting what? We are getting a G1-phosphate. The glucose is still trapped. Now, that's very important to know. Now, why glucose 1-phosphate instead of free glucose? Why not just get free glucose, right? If glycogen phosphorylase, this enzyme right there, right? If this enzyme, glycogen phosphorylase kinase, right? If this enzyme releases free glucose, the cell would immediately need ATP to phosphorylate again if it wanted to use glycolysis for future, right? For energy saving, right? So instead, nature is like, okay, I'm gonna keep it this product of whole glycogenolysis, the product as glucose 1-phosphate. It's like a nature saves energy, right? It releases that glucose 1-phosphate. Now later, this enzyme which is called as what? Again, we have this enzyme glucomutase. Now this phosphoglucomutase, this enzyme actually converts glucose 1-phosphate into what? Glucose 6-phosphate. Right? It converts that to it. Now here in this step, notice that we don't need any ATP. The phosphoglucomutase, right? There's a one continuous word. Now phosphoglucomutase, no ATP needed here. That's important, right? So let's put some light on this whole thing that's happening. Now I really want to put modulin and calcium in this picture. Now let me do it slowly, and I will do this in the second part of glycogenolysis. So this whole process actually started with glycogenesis. I thought I would go in that direction, but it turns out that we actually went to glycogenolysis because to understand glycogenesis, we want to understand glycogenolysis first. Okay, so let me end the video right now, right? And I hope I'll be able to make second part.